now it's my pleasure to introduce Aswin. He's professor at electrical and computer engineering. And his specialty is in optics, has developed a long career in this area, and he's going to talk about computational optics for reality capture and 3D display design.
Thank you, Fernando. So Fernando mentioned my group works on what I call computational optics. So this is at the intersection of traditional ideas in computer vision, signal processing, image processing, along with optics. And in particular, what we've been doing for over a decade here is to build new systems where the design of algorithms and optics go hand in hand. And today I'll briefly talk about some of the work we've done in reality capture and 3D display design. So why these two topics? So if you think of the XR ecosystem, it spans a whole gamut of technologies, everything from capture at one end to display at the other, and of course even beyond that apps. But also all sorts of things in between, to the way the world is being modeled, the way content is being streamed and delivered and rendered in real time, all the modeling and all the optimization that goes into this space to, at some level, support this basic idea that you can take reality at one end, digitize it, transmit it to reality to the other end, right? So that's what one of my collaborators, Anthony Rowe, who will be here later today, and we sort of think of this as glass to glass or reality to reality pipeline. And as it turns out, much of what I do, and mainly because of the kind of research that I do, ends up concentrating on these two ends of the spectrum, both at reality capture or digitizing reality, and in display design, which is to take a digital world and bring it back to reality in a way that you can consume it. Okay, so what does reality capture mean, right? It means many things. At a high level, it basically means that you want to capture what you see at a fidelity that's acceptable, right? So here's an example of some early work we did a few years back. So what you have here is a high-speed video that we are decoding from a low-speed cell phone feed. And when you have objects that have very intricate motion, reality capture simply means you're trying to capture the dynamics of the object in all its complexity. And it looks like that, right? So here's another example of what this could mean. And let me see if I can switch off the lights. So here is the classic children's toy, Jack in the Box. Right? It comes out. You can barely notice, even when for those of you who played with it, you know how quickly this thing goes from being inside to coming outside. If you use a traditional depth scanner, this is like Kinect V2, time-of-flight sensor. This is what you see. It operates at at human time scales, 30 FPS, and you again see the Jack inside the box and then Jack outside the box. But to capture the dynamics of what's happening, right, you need to build high-speed 3D scanners. So with work with one of my colleagues in Wisconsin, Mohit Gupta, we worked on using what are called single-photon avalanche diodes, or SPADs, which can operate at extremely high rates and develop a technology of 3D scanning around it, which can capture at in thousands of hertz, 3D scenes, 3D scans of the world at thousands of hertz. Reality capture also means that we need to capture high fidelity appearance. So here is work that I did with one of my students. This work is almost a decade old now, on trying to capture shape, but also spatially varying appearance, here modeled as the shine and the reflectance of this helmet. And once you capture this object in all its complexity, you can then visualize it, render it, do all sorts of things with it. And we've also looked at capturing objects that are transparent, which are not easily scannable by traditional stereo or LiDAR-like technique or time-of-flight techniques. Here we use distortion of patterns and analyze it to build 3D models of this transparent object. Perhaps the work that's most related to XR systems is digitizing objects so that you can build a digital twin of something, right? So sort of the big difference between almost everything I've shown you before and traditional depth scanning or 3D modeling in computer vision is that in computer vision, always pose the problem as one of, give me the depth map of one view of a scene, right? And that's very useful if you're trying to navigate a robot, that's enough. If you're trying to run an autonomous vehicle, that's enough. But for anything that requires actual digitization of object, you need to build a digital twin, which means capture the object from all perspectives so that you can build a 3D model of an object that looks like this. Right? So in this one, we did it by putting an object inside a kaleidoscope and taking a photo of it. We built a couple of different scanners. One of them was taking a photo, other one was a traditional structured light scanner. But the high-level idea is that if I take a photo of an object inside a kaleidoscope, you see hundreds of views of the object. Right? You see the object from all sorts of viewpoints instantaneously. So imagine this elephant was well, a real elephant that was doing something inside this kaleidoscope. Right? This is the kind of imagery you want, instantaneous imagery of an object as it does whatever it's doing. Right? And with that, we can take these images and recover 3D shapes of the object by, in this particular example, we fit a neural model to it, a neural shape model. Basically what it means is we had a neural representation for the underlying shape, which we regressed by taking that image and making it match the observations there. And sort of, if you can build a digital twin, you can build a real twin. So then we 3D printed it. So here are those 3D printed objects. It looks nicer on a better contrast screen, so I'd encourage you to check the paper on that. So that's at one end of the spectrum, reality capture, right, where we are moving from the real world to the digital world. At the other end of the spectrum is display design, where we have content that we want to show, right, let's say a 3D model, and now we want to make a user see that 3D model. And much of this gets into understanding how we perceive the world, how we as humans see depth, color, intensity gamut, right, motion. And a display has to satisfy all of those cues for it to be, for it to sort of give you the illusion of reality. So one of the sort of the most dominant cues, so color, intensity, gamut, right, all of those things are very important problems. And but today's technology, like the displays that we have, they already provide a sort of a pathway to achieving what we need there, whether be it resolution, be it intensity range or color. Where things get really tricky is when we need to see depth, right? How do you make a 2D screen like this appear 3D to somebody who's viewing it? So we can look into how we see depth. One of the, as I said, the dominant cues that we use is called vergence. Vergence is this idea that if you put an object at some depth, your eyes verge on it, right? So that at some level, that object appears in the fovea at both of your eyes. And if the object is really close, for example, my thumb, your eyes are going to verge inside. If it's farther away, it'll remain unverged. And this gives your brain a sense of what is the depth at which you're seeing things. One of the oldest way in which 3D displays were built. So here is a 150-year-old set of photographs to be viewed with this stereoscopic display, right, which allows you to see each side to each of your eyes. And then when you see this, you sort of see the depth, right? And if you just flip through it, you can already see what the depth would look like. But your eye sees many other kinds of, many other ways in which it perceives cues. And all of them are very strong. One of them is motion parallax, right? If you close one eye and simply sort of move your head left to right, you'll see different objects move at different speeds depending on how far away they are from you. You see occlusion patterns revealed, right? Things that you're not seeing in one view that appear in another, which gives you depth ordering. Again, a very powerful cue for understanding the world. And then there is accommodation, which is the focusing of your eye. Your eye has a lens, and that lens can focus just like your lens in your camera. And depending on where you're looking at, whether you're looking at the front or the back, your eye changes its focal length so that that part comes into focus, it's sharp, and you get to enjoy the world. And sort of the gap in technology comes in the sense that today's displays are stereoscopic, meaning they satisfy the vergence cue, but they largely treat motion parallax and accommodation. They leave it either as something to not worry about, at least for now, or something that you take care of by rendering in real time, especially motion parallax is something you can handle via that. So why is this a problem? So imagine a stereoscopic display, right? So think of your favorite display. It's showing you two different images, each one going to a different eye, and then you see the depth in the world by simply the relative placement of an object in each of your eyes. Okay? Now, when you put the tree at some distance, you expect to see a tree there. Your brain believes there's a tree there, so your eye focuses at that distance, except there's nothing there. Right? All the content is coming from somewhere else where your display is designed to put content in. So this produces this asynchrony between two dominant cues by which we perceive depth. Divergence, which is the steering of your eye, and accommodation, which is the focusing of your this thing. And this causes, and this has been well established in literature, it causes visual discomfort, but it also reduces resolution because when you observe something in defocus, there's going to be blur, and blur is loss of resolution. So we've been working on display designs that sort of flood your eye with content coming from all possible depths, right? To the extent that we want to fool your eye in thinking, at least from a depth perspective point of view, that the content is coming from like almost a continuously varying world, right? So that's one of the things we've been working on. And as it turns out, these kinds of displays can be built with small modifications to today's displays. So, if you buy any of the 3D displays available today, it's basically this design. There's the display, and there's an eyepiece which places the display at some fixed depth. One of the early designs that we explored was a display that changes this in two ways. It looks the same, a display and an eyepiece, but we make the eyepiece focus tunable, and we track its focal length in real time, so we sort of let it go through all sorts of focal lengths very, very quickly, and we synchronize it with a high-speed display, and we show that this kind of a design can give you very realistic 3D content. It looks like this in our lab setup. So you have a camera here that's sort of playing the role of your eye. So I'll show you imagery from this camera. This camera is not connected to the display. The display itself has two main components, a high-speed projector and a focus tunable lens, which has a focal length tracking system baked into it. So here is some focus stacks captured from the camera, right? So what is a focus stack? Imagine you take a camera, capture its focus ring, and you spin it while taking multiple photos. So you expect to see different objects at different depths come into focus and then go into defocus as you sweep back and forth. So using the camera I showed you in the last slide, we capture the focus stack of this particular scene. Right? Again, the other thing that we have to worry about is motion parallax. Imagine you move your eye left and right. Right? What you want to see is realistic motion, realistic occlusion, and for reasons that I'm not going to get into because in this talk, in sort of the interest of time, the illusion of reality breaks down in today's sort of, if you build a multifocal display like what I showed earlier. So to the extent that, so here is an example. This scene has content coming from two depths. One depth has the red content, the other depth has the green content. And all I'm doing is mimicking the motion parallax scenario where you move your eye left and right, move your head left and right. And it's hard to see, in the absence of occlusion cues, it's hard to see which one is in front and which one is behind, right? Depending on where you focus, either of them can be in front and, or behind. So how do you build these kinds of occlusion cues in our display? We developed this display that we call cone tilt. What cone tilt does is, in reality, in real world, to mimic occlusion, you need to block light rays. We showed that if you can tilt cone of lights with certain degrees of control, then you can build the same effect as light rays being blocked because these light rays are never emitted. And this gives you a display, and these are all actual results from a display, that can take that scene and make it look like that. And hopefully it is now clear which one is in front. Fernando, which one is in front?
No, both of them.
This one?
Yeah, this one.
Anyone? Which one is in front? Red. Only two choices. You have one. You can get one wrong, right? And then this leads to sort of the holy grail of what we would like to do in display design is can we take a 2D display, this guy, and make it into a 3D screen, right? Without obviously building a 3D world here. Turns out there are ways to do this. I won't talk about underlying technology. It looks like this. But my student has a poster and perhaps a demo if she gets it working again later today. I haven't heard from her, so it's possible. She's still working at it, we dismantled it for another paper, now we're putting it back together. But the results look really cool. So here's a focus stack from this display, right? And I showed you the previous one, which was a few years back. This is a newer display. So this takes a 2D screen, sort of uses the idea that in optics, the difference between points light coming from different depths has to do with the nature of light the nature of the wave that is being generated. So we use that idea to take a 2D screen, and on each point we induce the right amount of delays so that it appears like a 3D object. And with my colleague, Matt O'Toole, who's a faculty in the Robotics Institute department, we sort of rigged the game around it. So you can play this game in 3D, right? In real time, it renders all the content that you need so that, it's a 3D scene that you're looking at, and it's on a 3D display, all rendered real time. Hopefully, you'll be able to see this. If not, there's a poster. You can learn more about this. Now, before I sort of end, let me talk about some of the educational sort of work going in this space. So as I said earlier, I work at two ends of this pipeline, and my colleague Anthony Rowe works on everything in between. Right? And we suddenly had this realization one day that we complete each other. And so we decided to put together a course that spans a whole gamut of technology that spans XR systems. This is the first time we are offering this course this semester. And we are covering everything from starting with the idea of what is this reality continuum, what is XR, MR, AR, what are all the technologies that goes into this, and then working our way through human perception to display design, to reality capture, localization tracking, real-time rendering, collaborative environments, the whole gamut of things, or at least a selection of things that we think are important. Not that others are not, it's just that we have David doing a lecture on HCI, things that we don't know ourselves. And many others. Larry gave a lecture earlier on drama and how XR interacts with it. So with that, I'll stop, and I'm happy to take questions.